Hello everybody, welcome back. We're going to be looking at a different quiz this time. Still, I think, from section 4 actually. It looked like a good one. And once again, before we get into, full disclaimer, just because I don't go through a problem doesn't mean it won't be, that type of theory won't appear on your midterm. And just because I go through a problem does not guarantee that it will appear on the midterm. I'm going to try and mention that whenever I can, because this should not be how you study. This should be a little supplement to say, you know, I'm a little stuck as to how to start these questions, how to think through things. You know, give me the benefit of your having done linear algebra before, or, you know, being the prof for linear algebra. This should not be, I'm just going to watch Professor O'Hara's videos and I'll be done. You know, that'll be fine, I'll just memorize that. No, it's not how it works. Anyway, let's get back into it. We've got another quiz in this set of videos, or in this video. And as I mentioned, Section 4, whoever makes Section 4 quizzes, I'm liking their work so far. Although, I think we got a little bit of a typo, because this was quiz 2 for them. At least that's how I have it recorded with my stuff. But it's a little longer. Still 2 questions, but they had to use 2 pages here. Okay, so question number 1, it's a 3-parter. Consider the following system of linear equations. Ooh, I remember that stuff. That's 2.1 in the textbook. Okay, so we've got a nice system here, 3 variables, and we're just being asked to write down the augmented matrix for the above system. It's usually, I mean, they've got 2 marks here. I would probably only give that a 1 mark, really. You guys are experienced at doing that. So basically, and we try and remember, why do we bother with augmented matrices? Because when we're solving a system, as long as we agree to keep everything in the same order, we don't really need all the x1s. Okay, you can just write 1, 3, and 1. We don't really need the x2s, we don't need the pluses, all that stuff is irrelevant. All we really need are the coefficients and to be able to manipulate them in a nice, efficient way. Okay. And then what have we got? Negative 1, x3, negative 3, x3, but oh, no x3s here. Why, that's a 0. And then the equal sign turns into just a nice little line, and negative 3, negative 7, negative 3. Okay. So there we go. And now B part, use Gauss-Jordan elimination to find the row-reduced echelon form of the matrix obtained in part A. And if we look ahead, we will even be asked to actually solve the system. Well, okay. They're just breaking up into parts what we would do anyway to solve the system. And you don't use guess and check at this sort of level of mathematics. So Gauss-Jordan elimination, I want to row reduce. Okay. So, well, I've got a leading one up here. So I'm going to use that to cancel out everything else. So row 2 minus 3 row 1. Why is that? Well, because I got a 3 here. And how do you get rid of a 3? You subtract away 3. And I mentioned this in class a long, long time ago. But yes, show all your steps. No, don't combine steps. So, should hopefully get a 0 right away. 7 minus 3 times 2 is 6. Negative 3 minus 3 times negative 1 is 0. No, something's wrong there. It's... Oh, no, it is, because they both have the same sign. Okay, yeah, so that's a 0 as well. And then negative 7 minus 3 times negative 3 is negative 7 minus negative 9, and that's going to end up being a 2. Okay. Now I'll use my leading one to get rid of the 1 on the bottom row, so that's row 3 minus row 1. The 1, 2, the negative 1, they stay where they are. Negative 3, 2. First 2 rows are unaffected, but it's row 3 we start getting rid of things. 0, 0, and 0 minus negative 1 is 1. And we get negative 3 minus negative 3. Yeah, minus negative 3, so we get a 0 here. Alright, we're looking not so bad. We've got... a 1 and 0s everywhere else in that column. So that's done. We move over and we ignore the first row. The next row that is non-zero is row 2. We want to get rid of this 6. How do we get rid of a 6 and turn it into a 1? We multiply by 1/6. 1, 2, negative 1, negative 3, 0. Not 6 anymore. Now it's 1, 0. 2 over 6 is 1/3. I get 0, 0, 1 here, and a 0 here as well. Okay, we're doing great. Now we've got a leading one here. We're going to cancel this 2 out. So we'll do row 1 minus 2 row 2. 1, 0, 0, 1, 0, 0, 1. Negative 1/2. Ooh, no, sorry, 1/2. 0. And now we get rid of the 2, so it should go to a 0. Negative 1 minus 2 times 0 is just a negative 1. Negative 3 minus 2 times a third. Okay, negative 3 minus 2/3. Well, that's negative 9/3 minus 2. So it should be negative 11/3. It's okay to do side calculations. Try not to let it clutter up your main body of work, but if you need to, and I know especially when it comes to, for example, doing things in, say, Z2, Z3, where we have to find inverses, finding your inverse on the side is a great thing to do. Remember, you can't divide in Z5 or Z3. Not that this question had anything to do with that, but just a gentle reminder. Okay. So, we've got one more thing to do. We're almost row-reduced echelon form. We've got this nice little staircase of leading ones, as I'm fond of pointing it out. We have no 0 rows to put on the bottom. The only thing that's a problem is not every leading one is the only thing in its column. We've still got this negative 1 here. So, what do? We add row 3 to row 1 to get rid of this minus 1. Now we get 1, 0, 0, 1, 0, 0, 1, 0, 0 here. Negative 11/3 plus 0 is still negative 11/3. 1/3 and 0 here. Okay. Notice right away that we've got I3 here. Okay. What does this start to tell us? Well, if we wanted to start making connections to later parts of the course, this matrix here, 1, 2, negative 1, 3, 7, negative 3, 1, 2, 0, we know it's invertible. Okay. We even have a series of row operations. If we wanted to, we could write out the elementary matrices associated to them, multiply them all together, invert them, and we would get A. Okay. We don't need any of that right now, but hey, it turns out that we've got an invertible matrix on our hands. What can we see right away for our particular question C, where we want the general solution? Well, we could see, for example, something like, well, the rank of this is 3, the rank of the whole thing is 3, so we're going to get a unique solution here. That's one thing that we could note. Or we could just say, well, translate it back. x1 plus 0x2 plus 0x3 is negative 11/3. x2 is 1/3, and x3 is 0. Okay. So, with something like this, I might say, okay, I've got my solution, but me, I'm a little queasy. Okay? And it's not because I had a, off-colored dinner. It's because, I'm not the biggest fan of fractions. I always feel like if I'm doing a row reduction, I might have done something a little bit wrong. So what I'd like to do is take my answer and plug it back into the original system. It's just a great little check. Depending on the numbers, it can, take 20, 30 seconds. But it makes sure that all this work here was not for nothing. That I didn't make some silly mistake. And if I have, well, I can try and identify that. So what have we got? Well, x1 is negative 11/3, and we're saying plus 2 times x to the x2, which is 1/3, minus 0. And, okay, so that should be negative 11/3 plus 2/3. That's negative 9/3. Hey, that's negative 3. Great, that first equation is satisfied. Okay. Similarly, the last equation is satisfied too, because, well, if I've got no x3, I'm still subtracting off 0, so it doesn't really matter. Okay. And what about that middle equation, that all-important middle equation? Well, what have we got here? So I've got 3 times negative x, or negative 11 over 3, plus 7 1/3, minus 3 times 0. This is what's making me feel a little nervous. And yeah, I think I've spotted an error, and I made an error right at the start there, but we'll just carry through here. Negative 33, it's going to be negative 11, plus 7/3. That is not negative 7. So, incidentally, I did not plan this. I genuinely just made a mistake. I 7 minus 3 times 2 is 7 minus 6, and I just wrote a 6 here instead of a 1. So, is there anything I can do? No, I made that mistake too early on. It's all done. It's all over. I've got to do everything again. So, this is a fantastic example of 2 things. 1, check your work. And 2, write in pencil on your test. Okay? You write in pen, that's a lot of whiteout, or worse, because students tend to just scratch everything out. And if you start making it so that it's very hard for people who are marking to read, you can sometimes not get the marks you deserve. Okay, let's not erase all of this. 0's here, 2's here. This is just a 7, except he's not a 7 anymore. 2, 0, the line stays here, negative 3 stays here. And this was a 2, but now this is a 1. And I'm sure a couple of you out there were screaming at me that, no, it wasn't a 6, it was a 1 all along. But there we go. Okay. So, next step, well, we're still going to cancel out this 1 down here. Feel free to fast forward if you are not interested in seeing another row reduction and just want to skip to the answer. Second row stays where it is, 2, and we'll get 0, 0, and a 1 here. Incidentally, what am I doing? Row 3 minus row 1. And this becomes a 0 here. Okay, we still use these 1s to cancel out everything else, except now we don't have a 6 here to turn into a leading 1. We're already there. So row 1 minus 2 row 1, or 2 row 2. 1, 0, negative 1. And negative 3 minus 2 times 2 is negative 7. This guy here's a 2, 0, 1, 0, 0, 0, 1, 0. And now row 1 plus row 3. Get rid of that negative 1 at the top. Alright, nicer integers. Still completely invertible. So my earlier comments still stand. But now what do we have? We've got negative 7, 2, and 0. And just to make sure I haven't made a third mistake, gosh, that would be embarrassing, let's double check. So x1 is negative 7 plus 2 times 2 minus 0 is, negative 3. So this equation satisfied, so is this one. 3 times negative 7 plus 7 times 2 minus 3 times 0 is negative 21 plus 14, and that's negative 7. So, we're happy now. So that was question 1, a little longer because I made a goof, but boy, am I happy I checked, because I would have gotten the marks for A, a mark maybe for B for part of my row reduction, but I really goofed that up. And depending on the marking scheme, I might have gotten nothing for C. Now, usually we try and carry mistakes that you've made in earlier parts through, but that's not always a guarantee. Part of it is, how crucial is having gotten the B part correct, and, should you have been able to tell in B whether or not you were correct, those sorts of things play a role. But we try to carry things through, not all the time, but we do try, okay? We understand people make mistakes. I made mistakes. All right, so now 2. And here's where we get the theory. So I indicate whether or not each is true or false. On the old style quizzes, you had to provide short justification. Sometimes, some years we don't ask for justification, sometimes we do, but I like providing my justification, even if it's just verbally to you so you understand how I'm thinking through this. All right, so this one here, 2A. The matrix here is in reduced row echelon form, RREF. Well, remember there's 4 things you need for reduced row echelon form. First of all, it has to be in row echelon form. So you have to have all your sort of leading terms forming this nice little staircase, and your 0 rows are at the bottom. And so what else do we need? We need leading ones rather than just leading terms or leading pivots. They have to actually be ones. Well, we've got those ones. They form a staircase. There aren't 0 rows to put at the bottom, so we're fine. And then what's the final condition for reduced row echelon form as opposed to row echelon form? Your leading term has to be the only thing in that column that isn't 0. And that works fine up until this last one because he's got a 2 here. So, false. The third columns leading 1 has another non-zero term present. Present in that column, I might even say. So here I've identified whether or not it's true or false, but I've also been able to tell myself, here's why it's false. Here's how I understand it. Here's how I know. And that's how you truly can back up a true or false. Whether or not you have to provide justification on a final or, on a quiz or something, provide the justification in your head. Never just guess. Unless there's like 2 seconds to go in the test or something. Scribble down your true falses, whatever you need to. But try and think through it. Try and connect it to definitions and theory that you do know. And so what did I do for this one? They're asking, is this RREF'd? I remember the conditions because I studied or because I taught linear algebra too many times to count. I remember the conditions for reduced row echelon form, and I just go through them calmly and check, are each satisfied? And no, one of them wasn't. It was so close, but that 2 there ruined it for everyone. Okay, so B part. A homogeneous linear system could have no solution. Okay. Now, theory-wise, if we think about linear systems, we've learned in class, it's been mentioned as early as chapter 2, that you can have no solutions, 1 solution, or infinitely many solutions. However, it's only as recently as sort of midway through chapter 3 that we've been able to fully justify this and explain that this is exactly why you'll get no solutions, 1 solution, or infinitely many solutions. We needed subspaces to actually do that. Okay? But this question is sort of aimed at chapter 2 style stuff. And for linear systems, it's certainly possible to have no solutions. But homogeneous systems aren't your average linear system. Okay? They're very special. And we have to remember, okay, what is a homogeneous system? It's one where you don't have a whole bunch of constants, you have a bunch of zeros. Everything's, a nice hyperplane equal to 0. Hyperplane equal to 0. Linear equation equal to 0. Linear equation equal to 0. And we might remember them as it's your coefficient matrix and then zeros. Or since we tend to work on Blackboard, we usually have 0 with the hat on it. But your textbook tends to use 0 with the bold. Okay. And if we sort of remember, well, I'll just make a dummy system right now. Okay, you might say x1 minus 2x2 plus x3, I don't know, equals 0. So here's a homogeneous system. But the nice thing about homogeneous systems, and we had a theorem about this at one point in class, we didn't make a grandiose deal about it. We just casually pointed it out. But it has been something we've used from time to time. Part of it is part of that theorem goes to show that a homogeneous linear system's set of solutions is a subspace. But the interesting thing here is you can always get what's called the trivial solution. If I make x1, x2, and x3 0, a linear combination of zeros is still going to be a 0. Still going to be a 0. So you always get the trivial solution. So I might say something like false. You'll always have the trivial solution. I don't care what size. Is it 2 by 3? Is it a 10 by 56? You'll always have a trivial solution when you look at a homogeneous linear system. Now, so we know we could never have no solution, but homogeneous systems can have 1 solution, or they could have infinitely many solutions. Okay, and this has actually gone on to give us bigger theory. For example, one test for invertibility is A a square matrix? Is the coefficient matrix square? And is there only the trivial solution to this homogeneous system? If that's the case, then you're looking at an invertible A without even having to find the inverse. And I think that's pretty nifty. But of course, that's expanding on the theory. We've got our answer right here. False. You're always going to have a trivial solution, the trivial solution, the all-zero solution. Okay? So that finishes up B, which finishes up this quiz here. And that's going to finish up the video. So take care, happy studying, and I'll see you in the next video.